Thanks for joining. Today we have a really nice 1 hour of tech talk. So we will talk about AI vision. Probably most of you knows, but about a bit more than 1 month ago, we released AI vision models. These are multilingual vision language models in 2 sizes and with the state-of-the-art performance in their parameter size. And today we are going to talk about the details and technical innovations behind AI vision models. We have in total 5 short but very nice with the detailed lightning talks here from our team. We will touch about the data, our modeling, some challenges in the multimodal space, both for data modeling or evaluation. And we also explain like how we designed in general the AI vision models beyond just releasing or putting the models into the Hugging Face. But all before, I would like to start with a very short intro to explain how we start AI vision projects. In this small screenshot, you see where when we started. Actually, at the time of release, it was 9 months of really hard work. It was really like a lot of hard work put into together to AI vision model, because I think I should start with saying the multimodal research is more challenging than single modality text-only LLM research. Why it is the case? Because first of all, if you look at the vision language model in general, multimodal papers or the models, there are much more experimental ideas about the architecture, about the training recipe and everything, right? So this kind of tells still there is a room to make things standardized. So there's much more ideas, which is nice, but also showcase much more challenges there. There are public data sets, but most of them are unfortunately low quality, and they are not really designed for real world use cases. And the evaluation in the multimodal domain, especially vision language domain, is extremely tricky. So it is very sensitive to prompt design. It is very sensitive to how you extract it. And it's, again, probably most important, it is not really addressing the real world use cases or use cases in the wild. But also it was even more challenging for our labs because our infrastructure was built to train state-of-the-art text-only large language models. So it was not really built for multimodal large language models. So we had to build almost from zero. And from the beginning, we started with the multilingual objective, because this is really this is our really the main target when we started. But of course, when you have another we already have another modality, and now we have 23 languages. So it's not really linear, even it's exponentially increasing the challenges. So that's why we put lots of hard work to the AI vision models. But of course, all the great challenges comes with the high reward, right? So it's not about complaining about those, but I would like to mention all this because I would like to give a huge shout out to the AI vision technical team here. So there are lots of people involved from our lab, even beyond, and from the Cohere. So that was really nice collaboration across multiple people. Even beyond the core team, many people actually helped us to build these models, to train these models, and to deploy and serve these models throughout the 9 months. So now I will pass it to Oliver, and he will talk about what we did in terms of data and evaluation.
Hi everyone. I'm Oliver. I'm currently a research scholar at Cohere for AI. So today I'm very excited to talk about AI vision today. Let's get started. All right. So first, I think most people here in this meeting room should probably already very familiar with instruction tuning for language model. So language model, by training on such data, usually the language models learn how to follow instructions and know how to give correct response and answers. And so for the vision language model, same thing here. So we collect a large set of vision language task data sets. In this case, they might be visual question answering, captioning, and so on. And then we use them to instruction tune our model with images. That's one more modalities. So, and just like what happens to the language models, instruction tuning not just teach vision language model how to follow instructions, read image, but also this process brings strong transfer and generalization capabilities. But here's the things. When we take a closer look at this general vision language task datasets, we will notice that they are very short in length, especially their response, usually a single word or phrase. And that's because these datasets actually were not originally created for instruction tuning or for training a large vision language model. Most of them were designed or borrowed from to develop specific visual capabilities in neural networks, like 3 or 5 years ago. And some were even built for for doing classifications. So, but naturally, these short one-word answers just don't match what people expect from a chatbot these days. Like you use ChatGPT, they are too brief. They are not very human preferred. And what even worse is training on such kind of data could lead to very severe model's text performance degradations. So to address these issues, we turn in our IO project, we turn to use synthetic data generation and knowledge distillations to help with this issue. So as I mentioned previously, so at first we started by collecting a large pool of task data sets. So each sample in this data set is actually corresponding to one specific task. And every specific task should have its own specifications. For example, if we are working on reasoning data, we might want to, generally now these days, we might more detailed chain of thought style explanations. On the other hand, for something like chart or table understanding, we sometimes want model to help locate specific cells or details, just walk through us the calculation step. So to make this happen, we create a task-specific prompt template for distillation here. So this template will ultimately ideally guide the process as the prompt model to generate very detailed response as our request. So overall, this pipeline generally gives us a more detailed, more natural, and more human-preferred instruction tuning data. And as the name of our project suggests, of course, in this for IO vision, we are aiming to build a really multilingual vision language models, which means we are absolutely need a multilingual, multimodal data. But the harsh reality here is that there's almost zero multilingual data out there for vision language tasks for open source. That brings us the next challenge. How do we create high quality multilingual data from scratch? In this work, we are mainly focused on translating vision language data at scale. We started with our recaption data set, and first run through an open source machine translation model called NLB, no language left behind. So it's to get the initial translations, and then we take the things a step further by rephrasing those translations using our coherence command R models. Now, we might start wondering, what is rephrasing? Why isn't a simple machine translation not enough? So here's an example. We got a very adorable puppet in the image, and the image question is, what the breed is the dog? So as mentioned earlier, the original answer is just one single word here. So if we zoom into the completion part, let's see how our synthetic annotations turn the raw answer into a much more detailed and comprehensive, much more comprehensive response. But when we run through a naive and NLB translations, things started to fall apart. The translations here we can see some example. The translations sometimes often come with artifacts like incorrect word choice. Sometimes doesn't finish cannot even finish the translations. Stop in the midway. The quality ends up being all over the place. But that's not what we want. That's not ideal for training a multilingual models. So That's where we start to where our rephrasing steps comes in to bring back the data quality. So by using our command R to rephrase our translations, we are able to clean up all the artifacts and deliver a translation that's not just accurate, but also feel more natural and fluent in the target languages. So in this project, we also explored a few different ideas like image translations. So we got a lot of vision language data with multilingual text, but here's the catch. A real multilingual model should not just understand multilingual text, but also the multilingual image is very important for training the multilingual model. So for example, here from QA, we went back to this source data and translate the text to different languages, and then try to re-render the table image to create like a real multilingual samples for training. And another thing is like on the one lesson we learned along the way is that fine-grained text image tasks have a particularly challenge for training vision language models. So in fact, it was also the slowest hill to climb up for us. And finally, we got all of our data, but to achieve strong performance, we also need to carefully select and reweight them for better generations. So each important, another equally important thing is that balancing the multilingual data to maintain the English performance. On the right here in this slide, you can see how the big impact, like starting with a 40% and boosting to 58% after we start finding the correct mixtures. So building the data set is only part of our story. It's really just the starting point. As we work on this project, we quickly realized something important, like for the evaluations. Like there are tons of academic benchmark out there for evaluating vision language models. Just name a few: MMU, MME, MMVET. But here's the problem: this benchmark often too heavily focus on models' visual capabilities. They don't give us the clear pictures of how good a model response really are in practical sense. So at the end of the day, we believe the best way to judge a model's performance is through our human evaluations. Human is the best judge. That's why we also introduced AI Vision Bench as part of our release. It's a multilingual, multimodal win rate benchmark that we designed to really put our model out there to test. We use holdout image, which means the image is not seen in the training, and carefully craft out the prompt to challenge our AI vision with a real-world scenario. So this benchmarks can give us another angle to measure our progress and truly understand how our vision perform in the practical sense. Yeah, that's the overview on my end. Now I will hand it to my teammate Saurabh, going to take you see behind the scene, share more about how actually we build the AI visions.
Thanks, Saurabh. Yeah. Now that we've seen how we generated data for AI vision, let's take a look at how, once the data is generated, how we actually train the model. So as mentioned before, AI vision establishes a new state of the art in multimodal multilinguality. And the way we went about it was the standard architecture for doing a vision language model is you have a vision encoder, you have a connector that maps it to the space of the language model, and you actually have like a pre-trained language model that uses its internal knowledge to kind of manipulate these image representations. One of the things that has been highlighted in literature is that you need very high resolution input images so that you can extract the most amount of information from the input image, and then towards the end, the LLM can kind of decide what it wants to keep or it wants to throw away. But another aspect is that images come in various sizes and shapes, and it is very important that you kind of maintain their aspect ratio and you process it in an aspect ratio as close to the original image as possible. Because if an image has a square and you kind of stretch it and change its aspect ratio, it becomes a rectangle. And if you ask it, well, what kind of shape it is, it'll never be able to answer that it's a square, right? So that is why we need to have both these aspects, an accurate aspect ratio and high resolution. And just to clarify, we use the recently released SIGLIP2 models as the vision encoder backbone. Next, we come to the next step, that is, once we have these image representations, how do we pass them to the language model? And to do that, we use something called a vision language or vision text connector. And this is basically a couple of MLP layers that map representations from the output of the vision encoder, the input of the language model space. And since one of the reasons that we mentioned before was that we need to have a very high resolution for processing images, but having a very high input resolution leads to a lot of image tokens being passed to the language model. And some of this is redundant. To kind of improve the computational efficiency, well, we use a method called pixel shuffling, which basically takes, which basically maps downscales in the spatial dimension and upscales in the hidden dimension. So if you have a patch of 2x2 image patches, what you do is you collapse them into a single patch, and you kind of expand it in the depth dimension. The total amount of information remains constant because like you're increasing the depth dimension, but like when you calculate attention amongst these amongst these tokens, it's much more reduced so that it becomes like much more efficient. And finally, we come to the language model aspect of it. Since we're kind of building a multilingual, multimodal model, we would like to have a multilingual language model as the backbone, because it understands representations in these various languages. For IAVision 8B, we started off with Command R7B, which is a very strong language model with very strong instruction following capabilities and word knowledge. And we further post-train it with the IA expanse recipe. Again, shout out to John Dang for doing this and getting us a very strong multilingual model. And we use that as the initialization point for IAVision 8B. For IAVision 32B, we simply use IA expanse 32B, which is a very, very strong multilingual model. The training process is actually two steps. The first step is called a vision language alignment, where we kind of freeze the language model backbone and the vision encoder and only train this connector layer. The goal is to use a very high learning rate to kind of imbue world knowledge and kind of rapidly, you could use a very high learning rate to kind of train the model so that you are able to map representations from like this vision encoder to the language model. And the next step is the actual supervised fine-tuning steps, where you kind of train it to do multitask learning. And so that we collect this diverse data set that Oliver generated, and which has like multiple tasks, and the language model is kind of trained to like perform all of these tasks. And in this step, we kind of just keep the vision encoder frozen, but we unfreeze the language model as well. And we kind of train both the vision language connector and the language model to perform these tasks. Yeah, but once it goes through the vision language training process, what happens is that the distribution of data has shifted. Now it is trained to do some tasks, and it is possible that it is possible that the catastrophic forgetting takes place, and you forget how to do some of these previous tasks that the language model excelled in. And when you actually measure it on win rates on like some a benchmark like M-Arena, you see that against like the model it has started off from, the win rates has actually dropped, and there's like a large degradation, which shows the existence of this catastrophic forgetting principle. Now the question becomes, how do we actually retain the text performance? Because that's also something that we need. We want to balance this ability to perform vision language tasks and also keep its ability to perform text only tasks. And to do that, one of the things we could do is add a certain portion of like the text data in the data mixture. But then it becomes very, very complex, as you have to kind of manage these trade-offs and run expensive sweeps to understand what is the sweet spot between them. And one of the ideas that we had is, what if you kind of merge them? Because merging provides a very computationally friendly way of managing these trade-offs without like kind of running expensive data sweeps. So the idea that we came up with is you take the LLM of the vision language LLM of the VLM, and you take the original LLM that it started off with, and you kind of merge them with like a certain like an interpolation factor. And we actually see that if you perform this merging step, you see a big boost in like the text win rates. And you see that the model is starting to reacquire some of these skills that it had forgotten with this merging step. But one of the most interesting aspects that we saw is if you do that, it also acquires back some of these instruction following capabilities that the original model had. And you actually see a boost in multimodal performance as well, because like the text model is like much more verbose, and like it has like a lot of it's a lot more fluent in its generation, and it also like kind of draws upon these abilities after the merging step. Yep, that's all I had. And like for more results, Arash is going to take us forward. Thank you so much.
Yeah, thanks, Saurabh. So yeah, I'm going to be talking about sort of like how we went about evaluating AI vision and some of the decisions we made regarding the eval sets. So in terms of evaluation, we have the AI vision bench, which Oliver talked about a bunch previously. We also have the multilingual wild vision bench, which is basically the wild vision bench dataset that was originally released in this paper. Wild vision evaluating vision language models in the wild with human preferences, and just translated to 23 languages, given that we're trying to evaluate our model in a multilingual setting. And on the right, there's an example prompt. It's basically handpicked QA prompts from a much larger data set of model comparisons, so Wild Vision Arena. Also, as a note, we use Claude 3.7 Sonnet as our evaluator throughout. This is not the same evaluator as what's used in Wild Vision Bench, but there was a bunch of tricky decisions we had to make that John is going to talk a lot more about regarding what to use as evaluator in our setting. So in terms of results, AI Vision pretty much establishes SOTA by really punching above its weight class. On this plot on the left, you can see win rates on the AI Vision bench, and on the right is the multilingual Wild Vision. AI Vision outperforms both Gemini Flash 8B and even Pixel 12B, and you have win rates pretty much ranging from 52% all the way to 81% on the two benchmarks. So it's very clearly outperforming other competitive models in its class. Now, one thing we really care about, given the model size of AI and also the general target audience, is its usability. And it's really important to us how AI Vision 8B performs compared to much larger models. And it turns out that AI Vision 8B really outperforms models that are a lot larger, like Llama 3.290B and even Momo 72B. So on this plot, on the x-axis, you have the number of parameters in billions, and on the y-axis, it's the multilingual vision win rates, basically AI Vision bench. And pretty much, you really want your models to be in the top left corner, so as small as possible, but also as highly performant as possible. And as you can see, both the AI Vision models, the 8B and even the 32B, are kind of in that upper left triangle above the other models, so which is pretty nice and makes it a lot more accessible to a lot of people. Now we also have per language win rates. Again, you know, as you all know, we're targeting a multilingual model. So even when we deep dive into the language breakdown of these win rates, you can see that not only AI Vision outperforms other models like Llama 90B on languages outside of widely used languages like English, it also outperforms them on English itself. So here on the left, you have AI Vision 8B win rates versus Llama 3.290B, and on the right is just a comparison point against Pangea. on a multilingual wide vision bench. And across the board, it achieves higher than 50% win rates, which is quite nice. Means it's not really you're not really foregoing performance in any language by picking AI vision compared to some of the other models, larger models. AI vision is also on Arena. So if you go to LLM-as Arena and under the vision arena, you can check out how AI vision 8B and also 32B fare against other models. Overall, AI vision, these results pretty much match up with the signals we had from our two other data sets, so AI vision bench and also multilingual wild vision, which is quite nice because the whole point of crafting those data sets and choosing them as our main benchmarks is to get a signal as to how AI vision is going to perform in the real world when actual users are trying to interact with it, and LLM-as is the direct signal for that, or the direct playground for that. So yeah, AI vision 8B is pretty much on par with Pixel 12B, Llama 3.290B, and Momo 72B. And even in English, when you just look at English only, AI vision is doing pretty close to Momo 72B and Qwen 272B, which are far larger models. And it outperforms Gemini Flash 1.5 and Pixel 12B as well, based on the ELO rankings on LLM-as Arena. But so far, what we've been, in terms of the results breakdown, we've just been looking purely at multimodal win rates, so including images. But one thing we really care about, and as Saurabh alluded to, is we want to improve multimodal performance or have high multimodal performance while retaining key capabilities like multilingual text-only performance. And it turns out AI vision does not really lose any of its inherent text-only capabilities. Here on this plot, on the x-axis, you have the multilingual text win rates, and the y-axis is the vision win rates. And here you want your models to be in the typically top right corner, meaning you maximizing performance both in text-only regimes and vision win rates. And both IA models, IA 8B and 32B, they're up there alongside Qwen 2.5 72B, which is a good model, but it's far larger than both of them. Yeah, and another thing that Saurabh also mentioned is we kind of combine a bunch of innovations to get to the performance that we have for the 8B and also by extension the 32B. The data that Oliver really led the creation of gives us pretty significant boosts on the base model that AI vision uses. On top of that, we use merging, which Saurabh mentioned, and that also gives a pretty significant boost. The cool part about merging is that it's really cheap. Only the real cost is evaluation, but here it gives close to a 12% delta regardless. And even just simply scaling it up from 8B to 32B, the plot on the right shows the step-by-step improvement, but it's for the 8B model. But even just simply scaling up the model dimension, the model size, it gives pretty much 9% improvement in terms of win rates. And this is without having been trained to convergence, which I'll talk a tiny bit more about in the next slide for the case of the 32B. So yeah, in terms of scaling, there's significant win rate improvements as we go from 8B to 32B, which is not really a surprise since the model has more capacity to learn the data that's getting trained on. The 32B again continues to outperform larger models like the 90B Llama model, Momo 72B, but also Qwen 2.5 72B, which is a quite impressive model. As I said, the 32B training was actually cut a bit short due to lack of time and the tight timelines for releasing the models. But we're going to be releasing a fully trained to convergence update soon, and that's going to be accompanied by the technical report of covering the whole AI vision family. So AI vision advancing the frontier of multilinguality and multimodality should be released in the coming weeks. So stay tuned for that and the new 32B. But yeah, I'll pass it off to John to talk a bit more about some of the challenges we ran into for using LLMs as a judge.
Yeah, thanks, Arash. So yeah, one of the core things we wanted to do with AI Vision is get better multimodal evaluation. If you look at most of the recent multimodal model releases from a variety of model providers, most of the commonly used multimodal evals like DocViewQA test very simple question answering tasks. The only metric here usually is accuracy, whether the outputted answer matches the ground truth response. But if you look at the DocViewQA example question here, what you'll see is that the answers are quite short. And so optimizing for models to output, answers in this format, while is often good for measuring just raw correctness values if the model is able to extract the correct information, this is not a natural way of conversing with a chat trained model. And typically our best multimodal models provide a lot more fluent responses than what is shown in many of these benchmarks. But one problem with moving towards win rate text evaluation benchmarks given multimodal inputs is that it's not exactly obvious what we should do in terms of measuring these win rates. So in the text-only case, we know large language models as a judge is pretty well studied and pretty highly correlated with human preferences. So if you take a top frontier text-only language model and you perform win rates on them, you'll get pretty good results. But there's really few existing works for using vision language models as a judge for multimodal inputs for text generation, and even fewer in the multilingual setting. One of the things we hoped when going for this VLM as a judge evaluation was that good multimodal performance implied that particular model was also good at judging multimodal responses. However, something we noticed is that surprisingly, large changes that we made to training data distribution often had little or no impact on VLM as a judge win rates. So we wanted to take a deeper dive into the performance of the top VLMs in judging multimodal outputs. Luckily, something that was released by Meta 1 week before the AI Vision launch was multimodal reward bench. And what they basically did was they took a diverse sample of multimodal inputs and completions from various vision language models, and then asked human annotators, expert trained humans given very detailed instructions to provide ground truth human preference labels for these completion pairs. And it turns out that the best vision language models really have abysmal ranking accuracy. So the top model that they tested was Claude 3.5 Sonnet, and it only got 72% ranking accuracy. And what this means is that 28% of the time, the ranking provided by the best VLM as a judge that they tested would actually disagree with the human annotators, which means that a lot of the times you're just getting incorrect preferences from VLM as a judge. And just to give a perspective on how bad this is, if you look at text-only reward bench, so if you take the best text-only evaluators, LLM as a judge, reward models, what we find is overwhelmingly they're able to get 90% or more on accuracy. The top 25 reward models or judges on reward bench get over 90% accuracy. And the multilingual, multimodal reward bench, we wanted to basically translate many of the prompts and completions from multimodal reward bench into other languages, because originally they were only in English. And what we found is that most vision language models are even worse at ranking multimodal completions compared to English multimodal completions. So we see here across Gemini 2.0 Flash, GPT-4o, Claude 3.5 Sonnet, and Claude 3.7 Sonnet is that the average overall ranking accuracy across 8 languages is lower by a few points than the English ranking accuracy, which already wasn't super high to begin with. And so this provides a it's pretty challenging to perform evaluations in this setting. The best model that we saw, the best non-reasoning judge was Claude 3.7 Sonnet, which achieved around 78% English, 75% average ranking accuracy. And surprisingly, Gemini 2.0 Flash, which was #2 on Chatbot Arena Vision leaderboard at the time when we did this study, even though it was one of the best vision language models out there, actually did pretty bad, getting around 60% ranking accuracy across all the languages. And so, yeah, most of the VLMs are really bad, and it's still, I guess, an open question of, how we can improve automatic evaluation for multimodal inputs and text outputs. Something interesting that we found was that actually reasoning helps a lot. So reasoning models like O1, which use inference time compute, gain a lot of ranking accuracy just by using those extra tokens. So if we go from GPT-4o to O1 with low reasoning effort, there's actually an 11% gain in ranking accuracy. So this means in the future, it might be worthwhile to train multimodal evaluators that utilize more inference time compute to get better ranking accuracy. But even in this case, even when using O1 with high reasoning effort, we're only getting around 83% ranking accuracy in English and 79% ranking accuracy across all languages. So there's still a long way to go for getting really highly performant multimodal evaluators. So yeah, for iVision eval, we decided to use Claude 3.7 Sonnet because it was a lot more cost-effective as an evaluator for win rate evaluations. And the reasoning models just cost too much for large-scale evaluations. And so this is the reason why this was the evaluator that was used for iVision Bench and multilingual wild vision. And this is what we use for development and also just what we reported publicly as well. And yeah, with that, I'll pass it off to Shivalika.
Yeah, thank you, John. So yeah, everyone, now that you've heard about how we went about building iVision, I just want to talk about how we launched iVision externally and went about connecting the world with iVision. So as you know, iVision is a multilingual, multimodal model, and it's fluent in 23 languages. And a lot of the speakers of these languages are they're obviously all over the world, and they are in compute. A lot of them are in compute constrained places. And so instead of telling people to download the weights or maybe call this API, it's a lot easier if we could just say, hey, scan this QR code or text this number, and you can talk to iVision on your phone. And so that was the goal with basically launching iVision on WhatsApp. And yeah, so you can actually text iVision, you can send it images or voice notes, and you'll be able to easily interact with iVision on your phone. When we initially did this integration, we were obviously being so close to the model development process. We were like asking it initially simple questions like, describe this image, or what do you see? And when we actually opened it up to our community and internally within Cohere, we saw all the different ways that people were trying to use the model, whether it was for chart interpretation or cooking help or expanding the context and or OCR and translation. And so all of these insights were really useful in terms of understanding how the model is performing in the wild with actual users. And we kind of also used all this feedback to help the training process as well. Like initially, I remember it was struggling with chart interpretation or OCR and stuff. And so we kind of used those insights to improve the model on those tasks. And yeah, of course, the community, you guys were a huge part of this process. You helped us test iVision not only on WhatsApp, but also on Discord. Shout out to John for setting up the Discord bot. And yeah, all of this was like really lovely to see how people were testing it in the different 23 languages that Aya supports. Yeah, and yeah, in the end, the final result was really lovely. It was great seeing iVision responding to like, you know, all these different queries in different languages, illustrating cross-cultural understanding, and responding in English and lots of other different ways. And we also asked the community to help us with setting up, sharing examples that we could host on our Hugging Face space. And so I just want to give a shout out to everyone in the community for that. And like, this was really helpful. And we have actually incorporated all your examples on our Hugging Face space. And yeah, these are some snapshots of all the different metrics. We've had like 1.1 API calls, around 158K model downloads, 500 likes, 11K API calls on WhatsApp. Yeah. So it's been great seeing how people are using iVision, and yeah, and the feedback from everyone. And yeah, with that, thank you for joining this talk, and I'll pass it over to Ahmet for opening us for QA.
Thank you, Chiralika. Thanks, everyone, for really insightful talks and details about iVision. Yeah, we have about like 15 minutes, and we are here for answering all the questions. Yeah, the most important question, apparently, the WhatsApp QR code, which makes total sense to me.
Hi, thank you for the amazing presentation and congratulations on the great results. I just wanted to ask, I agree with the team on the fact that the current standard benchmarks are not suitable, but do you think there's still room for comparing with other models on something that already exists in terms of benchmarks, or maybe something that's coming out new? Because while the Cohere benchmarks are relevant and amazing, they're still sort of internal, right? If that makes sense.
Let me touch a bit, but I will then maybe Oliver or Beza or anyone from the team can talk more. One thing, just to clarify, we released already both iVision Bench and White Vision. So because that's really valid point. I mean, if the evaluation is only internal, that doesn't make any sense to publish these results. That makes sense. But we already released those. But also with the technical reports, we will also put some more benchmarks, although there are some limits, but we will put more, especially multilingual benchmarks comparing with other models.
Yeah, we are not just evaluating on our iVision bench. We are also evaluating. We will put in the paper. We also evaluate most of the popular academic benchmark as well. And as Ahmet mentions, there's also some other visions win rate benchmark. We also translate them into a multilingual version, and then we evaluate on those win rate benchmarks as well. Yeah, hope that answers your questions.
Yeah, it does. Thank you.
Yep, go for it.
Yeah, hi everyone. Thank you, Ahmed. This is really a nice presentation from everyone and really a great work. The 9-month progress seems to be fulfilled. I have 3 questions. First one is, what open source vision language model is used for multimodal synthetic annotation pipeline? If it's okay to say.
Yeah, I mean, the thing is that we use a bunch of models to generate these results. That's why actually it's not only one model, because it would be like a biasing one model only. Yeah, that's, I think, the information I can give, I guess.
Yeah, true. I guess because if you use one particular vision language model, you get the same style of descriptions out of it. Yeah. Second question is like, what is the decision behind choosing an LLB script in the first place and then using command R for refreshing? Because I'm asking this question because IR 2332B itself is a multilingual expert, right? Like it can do better at machine translation. That's what we used. But is there any special reason behind using an LLB plus and then command R refreshing?
Oh yeah. I probably can give a quick answer here. Like actually, so IR command all the tech. I think I don't know if I'm correct. Correct me here. I think all the multilingual technique we used to train IR is also used to command R, and command R is like more commercial and more like has been deployed in multiple like a production area, and it's much most importantly, it's a much larger model. Like
Yeah.
Yes, a much larger models compared
Makes
to
sense.
IR. Yeah, IR is more like a experimental, like from an experimental model from a lab. Most simple generally just command R is a much larger models. And the reason why we use this pipeline is like, so there's a we prompt the model with command R that includes both English and its translations, ask it to rephrase the translation for better quality, right? Since we are not directly prompting for the translations, we want to provide some reference ground truths to prevent the model from generating out of context output. That's the most important reason why we use this like two-step pipeline.
Yeah, makes sense. Thank you, Oliver. And the last question is, what is the sample size for pre-training and IFT you have used to train the model? Dataset sample size?
Maybe Saurabh can address this.
Yeah, I can take this. For pre-training, so since we only train the alignment layer, we use around 1 million samples. This is where we like kind of focus mostly on diversity rather than like task-specific objectives. For the supervised fine-tuning, it's around 3 million packed samples, like 1 million samples that sum up to like each of them is like 8192 sequence. So if you look at like just pure raw number of samples, it would be I guess few million, I would say. I don't exactly remember the number from the top of my head, but 3 million packed samples. That's because that's what is used for like the iterations and like that's what the kind of determines the number of iterations. Yeah, I guess like it was like around 7 million or 10 million, something around like that samples.
Okay, are these samples also distributed across each language, or?
Yeah. So if you remember the slide, there are three major buckets that we focus on. One of them is original high quality samples, like from the original data sets. The reason the rationale behind including those is because if you do any sort of non-win rate evals, which are very, very constrained and use very specific matching, like exact string matching. In VLMs, unlike LLMs, most of these evals are zero shot. So there is no notion of what kind of format it expects. So you need to add that during training so that it knows, like if you do like if you ask it the CVQA or like DQA type questions, what is the kind of generations does it need to do? The second one is the main one, that is the synthetic re-annotated data, which provides like the major boost in like win rate and conversational abilities. The third one is multilingual, which is generated from the multilingual pipeline. Over here, we kind of balance the languages because like we want like good performance across like all the languages. And up this is like except English. So all of the other languages, like the distribution is uniform. And this is also around like 30% of the training data. So like around 30, like if you count English, it's like around 66% and 35%-ish. 65 and 35 is like English to multilingual split.
Oh, interesting. Yeah, got it. One last question, adding on from what you said. Do you see that, let's say, if we distributed the same training sample size that is used for English across all the different languages, would it improve the model or would it actually reduce the model performance?
Okay, so your question is, if you had the same training volume for each of these languages.
Yes.
Is that what you're asking?
Yes.
So you're saying, let's say if I had, 5 million samples purely English,
Yes.
are you asking if I translate all of them, or like basically if I have
Yeah.
a
Distributed.
multilingual equivalent of this?
Yeah.
And do you want to translate, or do you want to rephrase all of these 5 million samples per language, or do you want to split across 23 languages?
Not split. I mean, same size across all the languages, equivalent.
Right. So you need to maintain a healthy relation, like a healthy distribution between English and non-English languages, because first of all, if you have the same volume, and like the amount of training samples and the training size becomes too large, and it becomes kind of very challenging to kind of iterate upon it. So that's one thing. Like you can't, like, for a given flop budget, you need to constrain something. So if I say that this is like my flop budget, and I can only operate in this regime, then you need to find what is like the right mixture that kind of gives you the best performance. And after a while, you see that if you increase like the distribution, like if you increase the multilingual percentage above a point, it doesn't lead to any improvements, kind of tapers out or like saturates. So that's also an observation we have in the tech report, which we'll be sharing.
Awesome.
You want to add something to this, Ahmet?
I mean, I would say if you have like an infinite amount of resources, probably you can increase more with the constraint of diversity. But if you have very little diversity in terms of the multilingual data, repeating them to increase the balance may not end up being better. That was the main thing. So we could, of course, translate all the data. I mean, translate and rephrase. But then we had to train much longer, with the cost of like a multimodal training is even more costly than training an LLM. So there are some constraints, and that's why we bound to 35 to 40, because that seems to be within the data that we have, giving the best multilingual performance without some kind of outbalancing the English and some academic performance.
Yeah, awesome. Thank you.
Also, if I want to add just one more thing to this, like just like since you kind of expect the model to be able to perform some sort of interpolation, right? If you train it in English, let's say, as long as you include like a certain percentage of multilingual data that kind of demonstrates how the same scenario plays out in multilingual scenarios, you expect the model to be able to interpolate between these behaviors, right? And if you explicitly train for everything, it's very prohibitive.
I think it can even extrapolate for different languages when it is exposed to this equivalent distribution across the languages for the same sample.
Equivalent distribution for the same language across the sample as well?
Like, for example, right now we are seeing this truck image, right, within the WhatsApp. So let's say we have the English caption of that, but we also have different languages caption. By teaching these different language captions for the same image, wouldn't it extrapolate for different languages? Because the understanding at the model space is kind of different, right, from what we understand?
You don't need to have it for all languages. That's what I'm trying to convey. It's like that would be prohibitive. If you have it for like a subset of languages, like for different subset of images, you have if you have different subset of languages, then it kind of learns to kind of like learn, and basically the LLM has like a certain understanding of like concepts, abstract concepts, which become language agnostic, and then it's able to kind of like apply these concepts in different languages. That's why you don't need to explicitly add every sample in every language.
Yeah, I mean, let's move on to another question.
Yeah, sure.
Feel free to reach out to us from the Discord or with the email. I think it would be nice to chat about.
Yeah, thank you so much, guys. Yeah.
Okay, let me say the question. What do you see as possible future work ideas, if any? So I want to give the floor to Beyza because she is also one of the most important member in the team. It would be nice to hear about this from her.
The future ideas? I don't know, Ahmet. I think you should have continued. Yeah, but those are personal, Saurabh. So I think we can still improve the data generation to train a better model, because the current one covers 23 languages and the performance is fairly good at these 23 languages, but there's always a chance to increase the amount of languages we cover. That's one direction we want to go. Also, we invested on generating synthetic data for this project for both multilingual and to improve the quality of the data. And we also want to take this direction further, and we want to generate more high quality data to train better model. And also we want to focus on the evaluation. Both Arash and John today discussed about how hard to evaluate the multi-model models. And we also want to focus on that part. I can say those, but maybe Ahmet and Saurabh wants to add more directions, or John maybe.
I mean, not much thing to add, but the one thing that we noticed, although the AI vision models are, performing state of the art from the benchmark that we measured, but the multilingual OCR is extremely difficult. This is also one of the findings from the Pangea paper. We kind of validated that. Even if it may be performing slightly bit better, but not there yet, even for 23 languages. I think that is one of the area that, as a field, we should focus more on. Data, as Beyza said, is the probably most important piece of it. And like this automatic evaluation, however, with the benchmarks or with the more real world scenarios as we did, it has still lots of limitations. I think this needs to be also resolved. I think that's it, because thanks everyone again. Thanks for joining us. It was really nice presenting our work, but also discussing with all of you about the details and the future works. Oh, if there's one last question, yeah, we can take it.
Yeah, thank you for your team for the interactive session. So I am joining from India and I have a software engineering background. I'm looking forward to contribute to the work Cohere is doing, especially in multimodal arena, because I have experience with Photoshop neural filters from Adobe, and I am passionate about the multimodal space. So I see that Shivalika already shared how she has done the open source distribution for this, and Saurabh shared that we can create a OCR dataset. But are there any more model contributions you're looking forward from the community? Any specific places that you welcome contributions on?
There are a bunch of projects actually in the IA expedition. Some of them focusing the multimodal scenarios. I think you can give it a look at them, or reach out to us in Discord, because currently we don't have another project directly follow up with the community connections. But definitely we are thinking about that, and we really want to push the state of the art further in that sense.
That makes sense. Thank you, Ahmet. Yeah.
Thanks everyone.